A sugar cube of neutron star material weighs about 1 billion tons, more than every car on Earth combined, crushed into a space smaller than your fingertip. That object used to be an ordinary star, just like our Sun. Every star's death is already decided by its mass, including the death of the star warming your skin right now. Stars die in 6 different ways, ranked here from strange to reality-breaking. Some become dim embers. One doesn't even exist yet. The last one erases light itself. Number 1. The white dwarf. This is the fate waiting for stars like our Sun. Over 90% of all stars in the galaxy will end up exactly here. When a sun-like star exhausts its fuel, it sheds its outer layers into a glowing shell of gas called a planetary nebula, exposing a small, blazing hot core underneath. One of the very first white dwarfs ever identified orbits Sirius, the brightest star in our night sky. Astronomers detected its presence years before they could actually see its faint companion. That core still holds roughly the mass of the Sun, packed into a sphere the size of Earth. A teaspoon of it would weigh about as much as a small elephant. Gravity wants to crush it further, but a quantum effect called electron degeneracy pressure holds the line. Physics itself is the only thing preventing total collapse. There's a hard limit on white dwarf mass. About 1.4 times the Sun crossed that boundary, called the Chandrasekhar limit, and the whole star detonates. Left alone, a white dwarf simply fades, cooling for what is essentially forever. That slow fade is where the strangest item on this entire list begins. Number 2. The neutron star. This is what remains when a star 8 to 20 times the Sun's mass collapses in a supernova. The collapse takes well under a second. A stellar core larger than the Sun implodes to city size in about 100 milliseconds, then rebounds in the explosion we call a supernova. All of that mass ends up crushed into a sphere only about 20 kilometers across, roughly the size of a city, floating alone in space. The crush is so extreme that protons and electrons merge into neutrons, and atoms simply stop existing as atoms. The entire star becomes one giant atomic nucleus. There's an old line that you can never trust an atom, because atoms make up everything. Inside a neutron star, that stops being true. The atoms are simply gone. Escape velocity there reaches a large fraction of the speed of light. Drop an object from just 1 meter up, and it would slam into the surface at thousands of kilometers per second. This is the object from our opening fact. A sugar cube of its material outweighs every car on the planet combined. It's the densest matter we can directly observe. Number 3. The pulsar. It isn't a different object. It's a neutron star caught doing something specific, sweeping a beam of radiation across space as it spins. Picture a lighthouse. As the neutron star spins, its beam sweeps past Earth on a perfectly regular schedule, and telescopes detect it as a rhythmic pulse of radio waves. The fastest one ever measured spins 716 times every second. A kitchen blender's blades don't come close to that speed. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell. Its signal was so precise that scientists briefly nicknamed it Little Green Men, suspecting it might be artificial. Their timing is so exact that pulsars now serve as cosmic clocks, rivaling the precision of atomic clocks built here on Earth. Pulsar maps were even engraved on the Voyager and Pioneer spacecraft, showing 14 pulsars as directional beacons, a cosmic address, in case anything out there ever finds them. Because their pulses are so reliable, networks of pulsars are now used to search for ripples in space-time itself, faint gravitational waves passing through our galaxy. Number 4. The magnetar. Same neutron star recipe, but with a magnetic field trillions of times stronger than anything found on Earth. Earth's magnetic field measures well under 1 Gauss. A magnetar can reach roughly 1,000 trillion Gauss, a difference almost too large to picture. At close range, that field is so intense it would theoretically distort the very atoms in your body, long before you ever got close enough to see it. In December 2004, a magnetar 50,000 light-years away released more energy in a fraction of a second than the Sun emits in 100,000 years. That burst of radiation was strong enough to measurably disturb Earth's upper atmosphere from 50,000 light-years away. It remains one of the most powerful events ever recorded. The energy comes from starquakes, the magnetar's crust cracking under magnetic stress so severe that it visibly distorts the neutron star's own shape. Magnetars are rare. Astronomers have confirmed only about 30 of them, out of the thousands of neutron stars cataloged so far. Number 5. The black dwarf. This one doesn't exist yet, not a single one, anywhere in the universe. It's a prediction, not an observation. A white dwarf cools slowly over unimaginable stretches of time, gradually radiating away its leftover heat until it eventually goes completely dark. Estimates suggest that process takes on the order of a quadrillion years. Our entire universe is only about 13.8 billion years old, nowhere near enough time. Our own sun will become a white dwarf in about 5 billion years. Even then, its countdown toward becoming a black dwarf will have barely begun. When one finally does form, it will be a cold, crystallized sphere of carbon and oxygen, invisible except for its gravity, a corpse with nothing left to give. Every detail of the black dwarf stage is a well-supported hypothesis built on known physics, not a direct observation. Nobody has ever seen one, and nobody will for a very long time. Number 6. The black hole. This happens when a star roughly 25 times the sun's mass or more collapses completely, and nothing stops it. Gravity overwhelms every known force. Matter is compressed toward a point of infinite density called a singularity, sealed behind a boundary called the event horizon. Past that horizon, escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses it, not even light itself, can ever return. Here's the misconception this entire ranking runs into. People picture a black hole as a cosmic vacuum cleaner, pulling in everything nearby without limit. Black holes suck in everything nearby like vacuums. They only pull as hard as the star's original mass did. If the sun vanished and a black hole of the exact same mass appeared in its place, Earth's orbit would not change at all. The danger is only ever about distance. Proof isn't only theoretical. In 2015, LIGO detected gravitational waves from two colliding black holes, confirming a prediction Einstein made a century earlier. In 2019, astronomers captured the first direct image of one. A black hole isn't really a hole. It's the most extreme thing gravity can do to matter, the true end state of density itself. 6 deaths, 1 cause. Gravity always wins eventually. Every star alive right now is running the same countdown. It's only a question of how loudly, or how quietly, the end arrives. Subscribe to Cosmic Scale for more journeys to the edge of physics. Next time, what actually happens when a supermassive black hole finally runs out of galaxy left to consume?